Welcome back. In this video, we'll be investigating buoyancy and apparent weight. Apparent weight is a phenomenon that objects tend to feel lighter inside of water and other fluids. You may actually be familiar with this if you're swimming and a friend of yours is trying to float on their back and they start to sink a little bit. It just takes a little bit of a push to get them back up. Certainly, it would be much harder to support their weight outside of water. So their apparent weight inside of the fluid is much less than their actual weight. We'll be taking a look at a similar scenario in this problem, so go ahead and take a look at the problem statement. In this problem, we're given a graph that shows us how the apparent weight of a box depends on how much of the box is beneath the water surface. And we know the dimensions of the box. And that's pretty much it. We're only looking for, based on this graph and these dimensions, we're looking for the density of the liquid in which the box is sitting. So let's start with the equation of the apparent weight, which says that the apparent weight equals the weight of the box outside of the fluid minus the buoyant force. Now this buoyant force arises essentially because of the water pressure. As you go deeper beneath the surface of the water, all the water down here, or all the little elements of water, I guess I'll call them, feel more pressure from all the water above them. So as you go down deeper, there's more gravitational force pushing them down as there would be at the top. Because it's a fluid, this force is transmitted in all directions. So if you push it down, it'll counteract in that direction, but in all directions equally. In particular, if we're looking kind of over here, the water over here will be pushed down from the water above it, but it'll start to push in all directions. And right next to the box on the bottom surface of it, it's going to eventually push up towards the box. And this is what's providing the buoyant force, pushing the box up, counteracting the force of gravity pushing it down. And this is why the apparent weight of the box is reduced inside of the fluid. Now, Archimedes' principle says that this buoyant force only depends on one thing, the amount of displaced fluid. So let me write this as the weight of the displaced fluid. In other words, how much water did I need to push aside to get this box inside? Whatever the weight of that water I pushed aside is how much this buoyant force is. And we can write the weight as a mass times gravity. Okay, now we have a lot of information about the dimensions of this box, so we can probably find out how much volume is displaced just using the fact that we know the area, and that'll also depend on h. So let me go ahead and write this mass in terms of volume times density, because that's going to give us quantities we were actually given and are looking for. So that's just mass's definition is the definition of density is mass divided by volume. So just plugging that in here, we have this formula. And so now we have the rho we're looking for, and we have some information about the dimensions of the box. And if I go ahead and plug that in, now first of all, I should just mention that this rho is remember this is the mass of the displaced fluid. So this rho is actually the density of the fluid that was pushed aside. The volume is the amount of displaced volume only. So it's not the full length of the box, only the part that's beneath the water surface, because this is how much water would be there had the box not been in its place. So it's pushed aside a volume given by its height times its bottom area. Area is given and the height is h. H means how much is beneath the water surface. And then if I just write that suggestively, let me write it like this. Rho Ag times h plus w. We see that this is actually very consistent with our graph. Our graph is telling us that there's a linear relationship between the depth of the box and the apparent weight. And we find the same thing here. It says the apparent weight is something times h plus another constant. So this is basically describing a line with slope minus rho Ag and y-intercept w. So this tells us that the weight of the box outside of the fluid is just given by this value right here, the y-intercept, which is 0.25 newtons. So this box weighs 0.25 newtons outside the fluid. Furthermore, we can actually find rho by equating this quantity to the slope of the graph. This just describes this line right here, and this is the slope, so if we find the slope from here, we can solve this to find rho. Let's go ahead and do that now. So let me write slope equals minus rho Ag, and solving for rho, we're given A, we know G. The slope we can just find from the graph. This is 0.25 and that's 0.1, so the drop is 0.1 minus 0.25 newtons divided by H, which is 1.5 centimeters, 0.015 meters. And then that's a slope. And then if I just retain the bottom part, A is 5.67. And that's times 10 to the minus 4. Remember, you're squaring centimeters, so it's 10 to the minus 2 squared, 10 to the minus 4. And then that's all times 9.8. Okay, and that should give you a value of 1,800 kilograms per meter cubed. So a very short problem. We just had to basically investigate the graph and then use what we knew from the definition of buoyancy and from Archimedes' principle. Let me just say one last thing about the right-hand side of this graph. So why doesn't it just keep going down? What happens right here? Well, this is what occurs when this entire box is beneath the water. Once the whole box is in the water and you keep pushing it down, you're no longer displacing any fluid. No matter how it moves around, the same amount of fluid has been displaced. So once you get to this point, the whole box is in the water, and as you push it down further and further, since no more fluid is being displaced, then your apparent weight is not changing. Now what this means is that this box, when you put it in the water, it'll sink of its own accord. And it'll sink until it gets all the way inside the water. And once it's inside the water, it will no longer feel as if it's 0.25 newtons. It'll feel as if it's only 0.1 newtons. So if you put this box in the water and then you try to hold it up when it's kind of submerged already, you only have to apply 0.1 newtons of force to keep it up. But keep in mind, it will sink. Once it's all the way inside the water, it still has an apparent weight. So it still has a weight. So unless something is pushing it back up, that weight's going to cause it to sink to the bottom of the lake or wherever it is. But of course, that weight will be much less than if it was above the water. And that's the notion of apparent weight. So again, a pretty straightforward problem. I'll stop there, take a look at the summary, and we'll see you next time.